Okay, I have the opportunity today to show you our Status 5 software, which is a software designed to do probability of detection study and also a sizing accuracy study. The purpose of doing the probability of detection study is to qualify an NDT method which is used for inspection. In general, for qualifying a method, you need to show its capability. And in many cases, the capability of an inspection system is evaluated based on the smallest size of the defects that the technique can detect with different level of confidence. So the way this study works is that usually designers would suggest a specific technique with a specific equipment, and then they try to use their technique to inspect structures or blocks with known defects, and then based on what they report after inspection of those known defects, they can evaluate that how their technique worked. To do that, when they do that inspection, our software is going to be used so that they can input their findings into our software, and our software can do calculation to demonstrate the capability of technique based on probability of detection curves, which shows the chance or probability of detecting a specific size of defect with that technique. To do that, if you start the software, you would notice two separate views. One view, which you can see at the top here, it's called the data view, which is the view that you can import or type in all the data that you collected based on your inspection. And the other view would be the chart view, which I will show you shortly, which all the results gonna pop up in that view. For now, because we haven't run any data, the chart view would just have our software logo. And what you can do, you can go change between the views. So you can have a full data view by selecting the data view option from this drop-down menu, or you can go to full chart menu if you just don't want to see the data. But in many cases, I personally find it useful to have both views at the same time, especially in the cases that you want to explain your graph based on your input data. So when you first start the software, the first step is to fill in your inspection data that the software is going to use to do the calculation. In this table, we have different columns that are associated with different aspects or different information about your inspection. The actual test data column is section which has 4 different columns that are all in blue. Is the section that you need to put input in terms of the actual size of the defects. The actual size of defects or actual test data are the actual size that known size of the defects in the blocks. So for depth, height, or length, any of those information that you have, you can fill these columns. Here, for example, as an example, in the first one, this refers to the defect that I already know based on, for example, the drawings of my block, that its height is 1.3 millimeter and its depth is 17.8. The other column here is a position, that it gives you a chance to give a position number or any indication in terms of showing you that what defect you're referring to. On the other side, we have exact same columns but under the title of inspection data. In these columns, if you want to do a sizing accuracy with our software, you need to fill these columns by the sizes that you would measure based on your technique, not by what you already know. For example, for instance, if you inspect a defect with UT method and you're using your you're just analyzing your data, when you use a 6 dB drop technique, when you use that and you figure out that the size is 16.9, and that's the size that you're going to report based on your analysis, this column is the column that you can input that data. And of course, you would see that there would be a difference between what you report based on your technique and what the actual size is. And the comparison of these two would be used there to do the assessment of your sizing accuracy. Again, we have the same position. We have the same position here, which would be the position that you would find in your analysis. This column here, the percent column, is a very important column, and that's where you report the maximum amplitude of the defect that you found. In most cases, the reason that the title is percent, and you can see that the measure here can be changed between the percent to amplitude or hit miss, is because when you switch to different NDT methods, you might not report the amplitude in terms of percentage. Usually for UT methods, always the amplitudes are presented in terms of percentage. But for example, if eddy current is used, the amplitudes are mostly reported in terms of voltage or just raw amplitude. And in that case, when you click on this amplitude, this title would be changed into the amplitude. But the important thing to remember is that this column is the column that represents the response, the maximum response, or I can say maximum amplitude response from the defects that you analyzed in your scan. The rest of the other columns, like operator, would be a good column to for if you wanted to, for example, compare different operators in terms of how well they did the sizing. You can add the name of the operators in this column and in front of their findings. The site, zone, and type are other columns that are available here to give you more information about the specific defect that you were inspecting. So for example, for for vertical inspection, US can be upside or DS downside. For zones, you can have different zones like root, lack of fusion, root 1, root 2. And for type, you can have the type of defects that you have. Is it lack of fusion? Is it crack? Is it vertical lack of fusion, horizontal lack of fusion, or any other type that you have? And the ID is also, again, can relate the defects that you inspected to your drawing that you have. When you finished all this, you put all the data that you have, now it would be the time to go and run the model to do a probability of detection study. To do that, we have a list of our models, our studies are here. So POD stands for probability of detection, and in the first section you see 5 different models. The difference between these models that you can see, you have one model called A hat versus A, but the other 4 models, Logit, Probit, LogLog, and CLogLog, are all categorized under one category which is called hit miss. The difference between these two sets of models is the A hat versus A would use the amplitudes that you put in this column directly for building the model. But the hit miss models would not use these amplitudes directly. But what they do is they compare these amplitude levels with the threshold value that you select, and based on that they categorize the defects or amplitudes in 2 categories of hit or miss. The hit ones would be the amplitudes which are higher than the assigned threshold, and then the software going to use those as 1, and the miss would be all the amplitudes which are lower than that threshold, which the software would account them as 0. For example, in this case, you can see that the threshold is already selected as 40, and in that case, for example, this amplitude 150% is going to be hit because it is higher than 40. But on the other side, this other amplitude, number 6, which is 38, is now going to be missed and going to be treated as 0. So if at the very beginning you have no idea about which of these models would be the model that you might want to use, we have this recommended model tab at the top, that by clicking that, all these models that we presented here for you would going to run automatically, and the software would do a calculation and comparison to do the assessment of which of these models fit better to the data that you imported. So here you can see the list of all the models that I just showed you and the parameters that can be used in those models. And in front of those, there is two columns of different values called AIC and BIC. And the AIC values are the mathematical parameter that that can be calculated for each model and be used as a representative of which model fits the best. And typically, the model that gives the lowest AIC value would be the model that best fits your data. So then, based on comparison of this AIC value, the software would directly recommend a model for you with specific parameters. So in this case, the LogLog model with parameter ln A is recommended because it had the lowest AIC value. And then you can directly click this button to go to that model if you just want to see the recommended model. But if you don't want to go to the recommended model and you want to try anything else, you can just close this tab and then go here and select any of the models you want. So to start, I want to just demonstrate one of the hit-miss models first, and then I will demonstrate the A hat versus A. So for example, if I go to the Logit model, then you start to notice that now in my data view, the graphs are showing up. So again, as I said before, you have an option of changing that to chart view if you just want to see all the graphs. But again, for the reason I mentioned before, that I always like to see both views at the same time, even a small one, I leave this data view up there. So here, this is the graph that is generated. So this graph is the POD graph. The blue line there show you, and if you look at this graph, it shows the POD, which is probability of detection, and it varies between 0 to 1. And you have also the size. Here, the POD is run on height measurements, on the height column, and it's used just the actual value, heights, and the amplitudes. But if you want to do your POD on depth, then what you need to do is to just check depth here. So if I change the measurement type to depth, now I would get a different curve, which this curve would be my POD result on the depth. If I want to go back to height, you again go to height. And you notice that none of our measurements here or sizes has unit here because we try to put the software to the unit list. So that would be your responsibility as you enter the data, that you need to keep the units consistent. So either you enter all this information in terms of inch or millimeter, but as long as they are consistent, the graph would be based on that unit. So we have two different, so here in this graph, that is probability of detection, the blue curve shows you the probability of detection of any size. So for example, if I want to know that what is my confidence in terms of what is my probability of detection of a defect with height of 1 millimeter. If I go to 1 millimeter here and go vertically to the graph, horizontally to the side, I would see somehow around some number around 0.8. It means that with this technique that I use and this input, there is 80% chance or probability that I can detect the defect with the size of 1 millimeter. On the other hand, on the other side, you can see another graph that this is basically the same POD graph that you can see on the left, but it is on the different scale. So here you can see that it is on a logarithmic scale, and the reason for that is to emphasize more on the tail of the plot, to basically emphasize more on the shape of the tail of the graph. Other than this blue line on each of these graphs, you also see a purple line. The purple line shows the confidence of your inspection. For confidence, you have the tab here that you define what confidence level you want that curve to represent. So if you change right now, this is defined as 95% confidence, but you can go and change that with this confidence tab to different numbers that you want, and as you change that, the model will run again and that curve will be updated. Similar to this threshold value, as we said, again, you notice on this curve that you have, on this graph, that you have some green points and some blue points. The green points are recorded as hit and the blue ones as miss. Hit is typically treated as a value of 1 and miss as a value of 0. And again, as I explained before, the way that these things are distinguished is by comparing your amplitude versus the threshold. So all these blue points are the points inside in the data that their amplitudes were lower than 40, so they're set as miss and they are plotted on 0 line. And the green ones are all the ones that their amplitude was higher than 40 and they're treated as 1. And then you can see those here. Always you can, on any of the graphs that you can see in status software, you always have a paragraph that paragraph explains that graph, and basically all the things that I tried to explain would all summarize in this paragraph. And you can see this in all other charts and other graphs that I will show you later in the software. And you have this option here to basically show those or not. So if I click this, then those description will go away, but if I want, I can click it to appear again. And that might be something very useful for reports. If you want to report this and you want to have a brief description of what the graph is, you can have that on. Other than this, there is other factor here that is called data type. Data type is just a mathematical selection that do you want to use the actual sizes that you have, or you want to pass the ln of those. The ln of the sizes is just a math operation. And again, if we don't have any idea of which of these to use, what can help us is that recommendation model. That again, you can compare and see when you use A or ln A, what difference you get in your AIC value, and based on that, the one that is the lower AIC would be the better one. So for example, here in Logit, it seems like using the ln A gives me lower AIC value, so it might be a better fit. So now I can use ln A. And in this scenario, you will notice that now my whole curve is going to be changed because now I use a different type of input for my model. The other important, so now that we have this POD model, now it's the time to get enough information, useful information that we want all of it for reporting and for qualifying our report, our technique. Those information are listed here. The information that you get typically is you want to know what is the size of the defect which has 50% chance of being detected, and what is the size of defect that there is 90% chance of being detected. So in that case, to report that size value, you need to just go to your curve and draw a horizontal line through the 50% chance, and the intersection of that line with your pod, which represents the crack size or the defect size with that height that has a 50% chance of detection. And that's what is also, you can see that intersection on the graph, and also the value is reported here. So for example, for this case, in this table, which is summarized, you can see that 0.3 millimeter is the height of the defect that you can inspect with this method, and you would have 50% chance of detecting that. Similarly, for A90 would be the size that has 90% chance of being detected using your technique, and in this case, that 2.44 millimeter. The other value here that we can see as NA, which is not applicable, is the intersection of your confidence curve with 90%. So in this scenario, based on the data, your curve did not intersect with the confidence curve, the purple one, did not intersect with 90% chance. So we cannot report that size. But if we change this, we might or we might not, when we change this graph, we might or we might not intersect with this line. So that would be another thing. But if we have a model that this purple line intersects with 90% chance of detection, that would be the crack size that can be detected by 90% chance and 96 or 98% confidence in the read. When you see these curves, the next options is, as you already know and I discussed, the most important factor to calculating this curve was the threshold value that you select. Again, when you change your threshold value, of course your curve is going to be changed, and also your data would be changed because now the input data is going to be compared with a different value. To give the users an insight in terms of what model fits the best, or how the threshold changes would change the graph, we have this show threshold optimization option. If you click that, new charts would be created here. That this chart shows the effect of changing the threshold value on the actual POD curve. So here you see that you have the legend here that shows different threshold values with different color, and as a result you can see all different POD curves. So each color here represents a certain threshold value, and the color associated with that on the curve shows you what type of POD curve you would achieve when you select that threshold value. And similarly, again, now I want to switch to my full chart view to see all these graphs together. Again, here we have our important lines, which is 90% chance and 50% chance, and the intersection of that line with all of our graphs going to give us the A90 or A50 for when we use that particular threshold. So here, that's how these graphs are generated. So you can see that the size of the defect with 90% chance that you can detect, how that would change if you change the threshold value in your POD curve. And again, if on some threshold values you can see those points, it's because your POD curve had no intersection with a 90% chance. So for example, this purple one has no intersection with this line. So of course, there is no A90 to be reported here. The other option that we have here is show convergence plots, and this is not related to the NDT, and it's more to get a confidence in terms of the model that we use as a correct model. These plots has no specific NDT use, but their main use would be to show that the mathematical model is correct. For a model to be correct, you need to reach a certain convergence of the model parameters. Beta 0 and beta 1 are the model parameters for the POD that shows that how well the mathematical model works. And here you can see that the math model worked pretty well, and after 8 iterations, we can reach to the convergence. And that gives us confidence that the model that we are looking at has been done correctly. And the last one is the likelihood, which again is another indication that how well our model worked. And the likelihood is calculated based on the parameters, optimized parameters, beta 1 and beta 0. And always the goal is you reach the maximum amount of that likelihood that by your iteration. And here you can see that you, from this low likelihood, you reach the maximum, and that then you get a convergence that your likelihood values don't change much. And the likelihood value is actually the value that is used for calculating AIC values, which were used in the recommendation tab to recommend a specific model. Then, if you want to, so all other binary models would be exactly the same and would exactly have the same set of options and same set of parameters. But the A hat versus A model would be a slightly different model. A hat versus A model is a model that, as I explained before, will use the actual, it's not going to use hit or miss, but it's going to use the actual amplitude values. That's why in the graphs for A hat versus A view, you won't see any of those green or blue points because there is no hit-miss data, and the actual amplitude values are used here to build this model. But here, still, the threshold is an important parameter because in the model, we categorize our amplitudes in 3 categories now. Below threshold, higher than threshold but lower than saturation, and higher than saturation. And that's why in this model the saturation number comes into a big role. The saturation is the value that you believe that higher than that you want to call your response as saturated. So in this case I just selected that to be 100, which means, for example, this number 3 data is going to be treated as a saturated data. Still, my threshold is 40, so still this number 6, which is 38 in amplitude, is going to be treated as lower than threshold. And 65, which is between 4 and 100, is going to be treated as a normal data between 40 and 100. And these 3 categories of your data are going to be used in the model. So now, similar to what you saw before, in the chart view, you can see your POD graphs. And again, of course, when we change these different parameters, we can have different curves. So here, for example, you see when I use a ln of the size and the actual amplitude, which in this case, the amplitude is defined as A hat. So A hat versus A is basically, the naming means the amplitude versus the actual size is used for the model. And A hat means the amplitude. So if I use the amplitudes and the ln of my size, this is a curve I get. And now here you see that in this curve, my 98% confidence also meets the 90% probability of detection. So here, if I want to report, again, you can see that, for instance, the height, the defect with the height of 2.14 millimeter is the defect that has 90% chance of being detected with 90% confidence interval. Here also, the crack that or defect that with the height of 1.16 can be detected by 90% chance, and the defect with height of 0.09 millimeter can be detected by 50% chance. Again, similar to the binary models, you have the show convergence, you have the threshold optimization plots that again show you the same thing, that how that curve, the POD curve, is going to be changed by changing your threshold. You have your model convergence plots, which is again the same plots that show you the convergence and calculates the AIC, with one difference that for A hat versus A model, other than beta 0 and beta 1 as the parameters, you have a delta parameter as well, so that's why you have 3 curves and a likelihood curve. And the other one is the show regression plot, which this regression plot show you, basically plots the amplitude versus height in different modes that we have here. So here this plot shows that how your data, which are these blue points, are plotted for height versus amplitude. So here if I again move to the split view, each of these blue points are the points representing a height and the response. So it's basically plotting the height column versus the amplitude column. But if you run further processing on them, like if you use the ln of the size, then the ln of the size versus the amplitude would be this graph. Similarly, if you use a ln of the amplitude versus size, or ln of both. And in each of these graphs, other than the blue point, you can see a red line, which is the best linear fit that can represent the behavior of changing of the height, amplitude versus height. And you can see the green lines that shows the confidence bands on the actual data, and the purple one that shows the confidence in the confidence band on the average of your data. So when we talked about all these models, you also note that there is another category here that you can see the exact same models, but under the category that's called Nordtest. Nordtest is just a European convention of how we treat the data before we pass them to the POD analysis. So again, the models that we use are exactly the same, but the difference would be that now in all of your models you would have another input to adjust for your model to run, and that input would be number of beans. And that's the only thing that is different by Nordtest. The number of beans means the number of categories that you want to categorize your amplitudes. So how it works is, when you select the number of beans, you categorize your amplitudes in 5 different levels. So 5 would be getting your minimum amplitude and maximum amplitude and divide them to 5 equal size, basically amplitude range, and plot everything in that. So these graphs here can represent the idea very well. So here you can see that because we selected the number of beans as 5, our amplitudes are all categorized in 5 different levels. So, for example, if the first level is between 40 and 60, any amplitude which is between 40 and 60 is going to be treated as 50, as average of that bin. And then we use this data now for the random model. This is basically a standard that was used before, especially when the computer speeds were low, that sometimes with large numbers and large number of amplitudes we couldn't get a convergence. So this was a trick to lower down the number of data in terms of their value to make the models converge faster. So here you, of course, when you do that, you can, your curve would change. So if I now change the number of pins to 10, it means that now my curve is changed and the information all get updated. And what it means is now my all my data are leveled in 10 different layers. So similar thing for the hit miss. So it's basically, I would say that the Nordtest is just the same purely analysis in terms of math, but it's another treatment of the data input for going to the model. After Nordtest, the next tool that we have here, so these two categories was the tools to calculate the probability of detection. The next tool that we have here in our software is the sizing tool, which helps to give a sizing accuracy assessment to the user and also to help to do a little bit of sizing optimization to their technique. I want to start by going over the sizing accuracy. The sizing accuracy study is now the study that the data which is going to be used for would be the comparison of the actual test data and inspection data. And this is really intuitive because with sizing accuracy, what our software wants to report is basically how well your technique worked for sizing a predefined or pre-known size defect. So here you know that the size of this defect, in fact, is 1.3 millimeter. But the way that you sized it is 1.2 millimeter. So this means it is pretty close. So what we do here in the sizing accuracy study is that we have two plots here to give us assessments, two plots and two charts to give us assessment of how well the sizing worked in our technique. In the first chart, it is a sizing accuracy regression plot. Again, we try to plot in blue points the measured heights versus actual heights. And again, you can do this if you want to do accuracy on depth, you can just switch to depth, or you can switch to height in this case. So in this case, each of these blue points represents the measured height versus actual point. So for example, if I look at this data point here that I show by my mouse, it means that the size that I measured in this trial was 3.4, while its actual height was lower than 1 or close to 1. So it means that here I did oversizing. Versus this point here, that its actual size was 2.3 millimeter, but the sizing that I did was closer to 1, so I was doing undersizing. So when you plot all these blue points, then we have a red line that shows the best fit that can represent their behavior, and the black line would be the ideal line which match the actual height to the measured height. So if you compare the red line with the black line, it can tell you that if you are doing oversizing or undersizing. So for example, in this case, the red line, which is the best fit of our measurement, is higher than that black line. So it means that for most of the cases, we did oversizing in our technique. And then the report, there is a report here that all different important parameters of that fit that can help in terms of assessment of the technique are reported here. And again, if you are interested to know the exact meaning of each and how they can use for assessment, you have two options. One, for the quick description, you can turn on the show chart description option that gives you all the description. And the other thing is that you can refer to our help pages. That in our help pages, we have a very, very well documented step-by-step explanation of what are each these means. The other graph that we provide in the sizing accuracy assessment is the graph that's called a scatter plot. Mainly the purpose of this plot is to show how our sizings are scattered or differ from or deviate from the ideal sizing. So the black line is again the ideal size. It means that it relates 2-point measurement to the actual height. So height up to measure 2.18 is the same as actual height. That's what this black line represents. The green line shows the band on the sides of the ideal that has plus and minus 0.67 millimeter off from ideal size, and the purple one is the one that shows plus and minus 1.34 millimeter off from the ideal size. So based on this, when we plot our blue points, here this graph can tell me that most of my measurements were within the green band, So it means that most of my measurements were within plus and minus 0.67 millimeter from deviation from the ideal. And that gives me assessment, again, another assessment tool of how well my sizing accuracy was done. And here, the table here, again, would give you a summary of how many of your measurements was within which sizing band. And again, this sizing accuracy can be well used to do the assessment on the technician. If you come back to your data view and in the operator, you input the name of the operators, like for example, you can say Mike or Pete or Oliver or anybody else that you might repeat this experiment, then what you can do, you can go to the filters that we have up here, show filter, and the filter, you can select the filter type here that we have, that we can go on, for example, operator, and the operator field, you can select Pete, and then the software would just show you all the results or all the results that Pete provided to you. And of course here the results are not enough to show you the graph, but I wanted to show you the concept that in that case you can compare the accuracy or capability of your different technicians, that which of them are better in terms of sizing and analyzing the data. So now if I come back and I don't use any filter, it's going to use all data. It's a good opportunity right now that I show you that these filters can work on all other columns as well. So you can select all different filters. If you just want to, for example, look at the lack of fusion type, you can add the filter and just look at those data. But when you run any filter, the data that remains in this chart, based on that filter, would be the only data which is going to be used for all the in software for the modeling and for the different studies. So after we do the sizing accuracy study, the next study that we can do is the sizing optimization. The sizing optimization study, the purpose of sizing optimization is help you to optimize the current sizing capability that you have. In this case, what happens is our software, typically when the technicians get the size, amplitude versus size, they use an equation or linear feed to try to indicate that what size would correlate to what amplitude. What our software can do is to suggest a new type of fit for that to be used as a calibration curve, so that can increase the accuracy of your sizing. For instance here, if I go through one of the examples, the first curve called linear least square sizing curve. In this curve, we plot the measured heights, the site that you measure, versus the amplitude response that you got from the instrument. Basically, use this amplitude response to do your sizing. So by plotting this and running the linear feed, this linear feed can represent any size based on any amplitude. Then this linear feed can be used to basically indicate what size you would measure based on your amplitudes. And when you compare that with your actual, you get this linear feed that compares with your ideal linear and show you how well you did the sizing. And ideally, if you change your initial interpretation of the amplitude versus size by changing the equation of this line, you might be able to trick the instrument to get a measurements way closer to the ideal line. And that's what we did here, that instead of using the best feed, we use other feed that we optimized, but this optimized feed would give you a result, measurement result, which much closely match with the ideal scenario. And this is based on a linear feed. And this is this would be the ideal suggested cal curve that is going to be suggested to you, that you use this equation for correlating your amplitudes to the sizes that you want to report as your measurement sizes. But also we have this one was a linear feed, but we could use a polynomial feed, power feed, and all other different feeds. But you can unclick this and first see the summary. The summary here compares different final optimized sizing curve compared to the ideal one, and the one which is closer would be the best one to fit. And here you see the blue one is the closest optimized sizing curve to the black one, and that blue one is coming from the power fit. So then you can just click on the power fit and find out what equation was used or can be used in the power fit for your sizing. The very last, and then after this, the last option that we have in this software is the noise study. For noise study, it's really important because the noise that you have, the background noise that you have in your analysis, that dictates that what is your threshold level. So if your noise level, for example, is 30%, your threshold, if you select your threshold value to be 20%, it means that you are going to call some noises as actual indications. So it's really important, and it gives us a guidance in terms of what optimum threshold value we want to use, so that we don't have any false call in our study. We don't call any noise as a defect by mistake. To do that, we have a separate column here, separate data, it calls a noise data, that you would have this column here that you select your noise data. So the noise study, all the things that happen in all the calculation noise study would run on this column of noise data. The noise data are the amplitudes on the locations in your scan that you are absolutely sure that there is no defect there. Again, the way that you can be sure is because you are doing all these on their well-defined pre-known samples. So you know those samples and you know the locations of defects, so you can bring your probe or your acquisition unit to the location that you're sure there is no defect there and record the amplitude. If you do that, that amplitude can represent as a background noise amplitude. And you need to at least have 15 random locations and 15 random numbers that give you that noise. And here in this case, I gathered around like 1 or 5, but the minimum you need 50 sample points. So when you do that random recording of the noise, then when you have this chart completed, then you can come to the noise study. And now I want to go to the chart view. And in noise study, first thing that the noise study tool gonna do is to try to analyze your noise data to distinguish that what type of mathematical behavior best represents the noise behavior in your system. To do that, we have 3 options: normal distribution math behavior, log normal distribution behavior, or VIVO behavior. In each of these, for example, now you're looking at the normal distribution behavior, we try to do the assessment that if our noise data behaves but or can be explained by the normal distribution behavior or not. To do that, here we try to categorize our noise data in, again, some certain bins and plot a histogram shape of those noise, and then plot the normal distribution on top of that and see how well it gonna fit the noise data. If you see the first 2 graphs, and again I want to emphasize that if this is not very familiar to you, again we have show chart description, that this description will describe exactly what you're looking at. So these 2 first charts are just a chart that give us a sense of indication of how well this black line or this behavior suits our noise data. For this, the first one, show this graph, the more linear this graph is, means that the data well behave to that study type or normal distribution. If you select that normal distribution and you suggest or you find out that normal distribution is the best, then the area under the curve of this normal distribution can be used to give you an assessment of what percentage of error or what probability of false call you would get based on selecting different noise level as your threshold level. And that is plotted in this curve. So in this curve, which is a probability of false call curve, show you based on normal behavior of a noise that each, for example, what would be the probability of false call that you would get if you use different noise level. For example, here you can see that if you choose 11.2% as your threshold, as a noise level that dictates your threshold, it means that you would have close to 80% false call. It means that your noise data is way higher than 11.2, that if you use 11.2 as your threshold, you're going to call many of your noise data as an actual indication. And that actual, for example, in a hit miss model, you're going to call them as hit. And that would affect your POD model. But this graph tells you that if you run a POD model with this threshold, you're going to have 80% false call in that, and your POD model might not be trusted much. But here, this graph shows you that if you use 30, it means that you will not have any false call. So in fact, in this case, if you chose 40, that it gives us confidence that we are not including false call, or our false call is minimized. But the same thing is happening that we check here for the log normal behavior and VBOOD behavior. But again, if we have no idea and we don't want to go to the details of this, what we can do is to just go to the analysis summary, and the summary table at the very end just tell you that which of these noise models, noise behaviors works best for your data. So here we say based on R-square value, noise data is best fitted to log normal model. So when you know the log normal model is best, you can just go to the log normal model, and based on the probability of false card, which is built based on log normal model, try to get assessment at what kind of threshold would be the best for you to use for your POD study. So this was the general overview of how our software works. Our software is designed to be really easy to use, and we have a very well documentation in the help pages. We have all these descriptions, but our team is also always ready to help you to use the software more efficiently and more easily. And if you have any further question, you can call Eclipse, and we will be happy to help you. I hope that you got useful information in this demo, and I hope that that covered most of the questions that you might have for using this software and helped you to use the software easier. Thank you.